Okay, we're now recording by the look of it, so good morning everyone. Welcome to Superconductivity Lecture 8. Let me just mention a couple of administrative matters before we start. First of all, as hopefully everyone's heard by email, but just to mention it in the lectures, we have a couple of changes to the dates and the venues for these lectures next week. That's because Wednesday is a public holiday and rooms are needed here for preparations for Peter Fulder's funeral on the Friday. So because of that, we've just moved both lectures a day earlier. So next week they'll be on Tuesday and Thursday at 10:30 rather than Wednesday and Friday. And because of that move, they will be in Seminar Room 1, the big hall, not this one. So please note that. That will then bring us to the end of the initially planned block of 10 lectures. It seems spectacularly unlikely that we will complete the advertised syllabus by the end of that time. So Andy and I have been discussing when we might manage to reconvene. Because of various travel commitments and workshops going on in the Institute that we shouldn't be clashing with and so on, basically May and June are not good. So we're currently tentatively planning to do part 2 in July. Probably starting July the 10th, maybe July the 17th, but keeping the Wednesday and Friday 10:30 slots. So we'll confirm all that in due course, but just to let you know that plans are afoot for a second part where we try and get to the end of the syllabus. Hopefully that will convince you that we're not under pressure of time, and so please keep the good questions coming. Actually, one of the most valuable things is that we're getting a lot of good questions, so please don't let that stop just because you can see the end of this block arriving. The end of this block is not the end. And who knows, maybe the end of the next block won't be the end either.
Yeah, then we'll have to get him back on sabbatical.
Well, look, I'm always open to offers. Good. So let's remind ourselves of where we were. We're nearly at the end of section 2, which is about superconductivity considered as a phenomenon of charged bosons condensing, but without asking where the charged bosons came from. And so far we've talked about how to write effective theories for that charged bosonic fluid interacting with the electromagnetic field, and we've emphasized how important it is that there's an electromagnetic field in this problem, and how in a sense, by gauge transformations, we can move any particular bit of physics from living in the superconducting order parameter to living in the gauge field. That's how we describe the Meissner effect, for example, by rewriting everything entirely in terms of the magnetic field. We've talked about some phenomena that predicts. So there's a coherence length in the superconductor, which is a direct analogue of the healing length in a superfluid. But there's also another length, the London penetration depth, which describes the decay of magnetic fields as you go into the bulk of the superconductor. And last time we discussed the fact that depending on the ratio between those two lengths, you can get quite different responses to applied magnetic fields. If the London penetration depth is short, then basically compared to the coherence length, then the superconductor is type 1. It keeps the field entirely out until it can't do so anymore and then just goes normal. Whereas if the London penetration depth is long compared to the coherence length, your superconductor is type 2, then the way it responds to a field is to introduce vortices, which then get more and more dense as the field increases and eventually overlap and the superconductivity collapses. A question was asked about how to calculate the lower critical field, the one at which the first vortex goes in. I have not yet looked that up, but I promise I haven't forgotten about it. And so at some point when I get a moment, I will sort that out properly and we'll come back to it. For today, though, I'd like to start with the last of the things I'd like to discuss before we talk about where these charged bosons came from in the first place. And that is the Josephson effect. Which, like learning that Mozart was composing symphonies at the age of 6 is the kind of thing that makes you feel inadequate. Josephson did the work on this when he was a graduate student, and it turns out to be pretty good work. The basic idea is that if a phase gradient in the bulk of a superconductor corresponds to a supercurrent, then you might think that a macroscopic phase difference between two superconductors would correspond to a supercurrent as well. Right? And the answer is that's basically right, and the Josephson effect is that effect, that if you have two superconductors glued together with a barrier in between, and they have different phases, we obviously have to be careful about that phrase because it's not gauge invariant, but let me say it anyway, and we'll discuss later how to do it properly. But the basic idea is if you have two superconductors with different phases, you glue them together with a little insulating barrier, then if the phases of the superconductors are different, then a supercurrent will flow across the barrier even with no applied voltage. And the supercurrent will depend only on the phase difference between the two superconductors. So this is evidence in an experiment that the phase is in some sense real, although we'll talk about what sense that is. So the system we're thinking of is this kind of thing. So I've got a superconductor here, which has some phase theta left, which I assume is uniform throughout the bulk of that superconductor. And we've got a superconductor here, which has a phase theta right, and we have an insulating junction, which we will think of as in some sense thin, although again we'll have to talk about in what sense that is. Obviously there has to be a barrier, or these superconductors would be connected and would be one sample. So we'll talk a little bit about what thinness means here. Now, you might worry about setting the problem up this way, because haven't we discussed the fact that the global phase of the superconductor is not a gauge invariant object, and so we shouldn't really be talking about it. The superconductor has a unique ground state. There is no actual degeneracy associated with this phase. Agreed. But it turns out that the stuff that we're going to write down that actually determines the current is properly gauge invariant and is related to the difference between these two phases. This is a bit like in single particle quantum mechanics, where the phase of the wave function of one system is not well defined, the phase of the wave function of another is not well defined, but the relative phase can be well defined and indeed controls interference effects if you then smash these two systems together. So the Josephson effect is about the phase difference across this junction. So delta theta, which is defined as theta right minus theta left, but actually that's not a gauge invariant quantity either, because as we know, gauge invariant quantities are always going to have to involve the vector potential and this phase, right? Remember, for example, expressions like the supercurrent, which is proportional to h bar grad theta plus 2EA, that's the gauge invariant combination of the superconducting phase and the vector potential, because it corresponds to a physical observable. And so we can't be writing things that depend only on theta. There must be some vector potential part here. And the answer is there is. The actually gauge invariant thing here is this phase difference plus the line integral of the vector potential on a path through the junction. Now you might worry what path through the junction, but if there's no magnetic field in the junction, it doesn't matter, because the flux through any closed loop is then zero, which means that any path that you use to integrate the vector potential will be the same as any other. So if we have zero magnetic field in this region, I can pick any path I like, as long as it starts somewhere in the right-hand superconductor and ends somewhere in the left-hand superconductor. Actually, the other way around. So if we are to speak properly, this delta theta is the one that we use. Now, if you open many books on the topic, or Derek Lee's lecture notes, for example, you will then find some argument about why we don't have to think about this term. So the typical argument is that if the junction is thin, this integral of A dot dl is proportional to the width of the junction W, and therefore goes to 0 in the idealized limit of a thin junction, and then we can just write the delta theta in terms of the difference of the phases. But clearly that's not really okay, because what it assumes is that the vector potential is not too large inside the junction. And there is nothing at all that stops you from making the vector potential as large as you like. There's a legitimate gauge transformation that just adds a constant to the vector potential, and so I can make the vector potential in the junction as large as you want. Yeah.
I understand why the path integral is constant when we are at some start point and end point, but if we move the end point and the start point, I don't see how it's inverted.
No, okay, that's right. So I've implicitly assumed that we're going to start at some fixed points here. Okay. I mean, if I changed those start points, then you have to think about what the gauge change would do to the phases in the superconductors. So in some sense, by saying that the phase is constant across this superconductor, I've already made some gauge choice. Right? I could have put a winding in the phase, made a compensating change in the vector potential, and the physics would have been the same. So yeah, it gets difficult in these problems to give a completely gauge invariant description, and we won't succeed in doing it, because at some point you have to write down a theta and you have to write down an A, and when you do that, you've chosen a gauge. But I'm just trying to point out that all of the actual physical observables, like the current that flows across the junction, do have gauge invariant formulations. People often, for convenience, pick a gauge in which the expressions are simple. And this is another such case. So you will see, and I'm about to write, the equation for the Josephson current across the junction as a function of this phase difference. But please keep in mind that there is a gauge I could have picked where it would have been written entirely in terms of the vector potential. It's just that gauge is a gauge in which fields are big and rapidly varying, and people don't like writing such things, but there's really no reason why you shouldn't. Okay, so the typical argument is not valid, or at least it's not gauge invariant. However, I'm just going to do what everybody actually does, which is to choose a gauge from the large family where this is negligible. But please remember that the observables I'm calculating would come out the same anyway.
Sorry.
Yeah.
Didn't you just say you've already chosen a gauge by saying the start and end points of that term?
Yeah, so I've partially done so, right? So what I've done by saying that the phase in this superconductor is constant is said something about what the vector potential is doing in here.
Yeah.
And what I've done by saying that theta left is constant is said something about the vector potential in here. Now I'm making a gauge choice which is about the behavior of the vector potential in the junction region. So in fact, in some sense, these statements don't uniquely pin down the gauge, they just restrict it. And then this statement restricts it further. Good. Okay, so I'm not going to derive the, yep, so please.
By choosing basically the phases to be constant and by that giving implications to the vector potential in the superconductor, is this creating, in some sense, boundary conditions for the insulating layer and the vector potential in there? I mean, I would guess that the vector potential still has to fulfill some continuity laws.
Yeah, that's right. I mean, yes, but it's consistent. Yeah, yeah, that's right. So if we write everything in terms of the point is that I can make an additive change to the vector potential everywhere in here by just making a winding of the phase. So what I've done is effectively pin the vector potential to some constant in here by saying that the phase doesn't wind, but which constant is still arbitrary. Yeah. Other questions? So I'm just going to write down the answer and give a rough argument for it. This is not, I mean, the only way I know to derive this is from the BCS type theory that we're coming on to next. So at the moment, I'm just presenting it as something that seems to follow reasonably logically from what we've already discussed, and that you should know that superconductors do. So the question is there a current across this junction? And there could be, because there is a gauge invariant object which is related to, which relates the two superconductors on each side and which could take different values in different physical situations, and so which might control a current across the junction. So let me just give a rough argument of two properties that, if there were a current across the junction, it would have to satisfy. If the phase difference is very small, then the current from the left lead to the right lead should be proportional to the phase difference. And the argument for that is that if the phase difference is very small, then there's not really much of a difference between a finite phase difference and a phase gradient. And then we're back to the formula that we had in the superconducting bulk. And so for this to be consistent, if I just take a bit of the superconductor and consider it as the junction, it must be the case that at small phase differences, the left to right current is proportional to the phase difference. The other observation is that the phase difference is defined only modulo 2 pi, which means that this left to right current should be a periodic function of delta theta. So we're looking for something which is linear when the phase difference is small and is periodic. Any suggestions?
Sine of theta.
Sine, right, that sounds good. Okay, so this is the famous expression for the Josephson current in a junction format like this. There is an interesting prefactor, this IC, which this argument does not predict. And that is the critical current of the junction. Right? So these arguments tell you that the current, if it exists, should be a periodic function of the gauge invariant phase difference between the two sides. There are good arguments that that should be, well, a simple choice would be sine. It turns out that's right. But this argument doesn't tell you anything about that prefactor. And in particular, it doesn't tell you it isn't zero. Right? And so we can argue that if this effect exists, then it should have this form, but we need to do some more microscopic calculations of the type that we're about to start discussing to work out what that critical current actually is and how it depends on the junction properties.
Could you say again what you mean by the gauge invariant delta theta after all the meandering or the agonizing we did above?
So this is this expression.
Okay. All right, okay.
So that is a legitimate gauge invariant dimensionless thing.
And you have no way of measuring that delta theta unless you're observing the current.
Precisely. So effectively, you can almost regard that thing as being operationally defined by this equation. But it has a definition in terms of the entities in the action for the theory.
I don't see why delta theta is defined only modulo 2 pi, because if it's only the port with the theta R and theta L, I understand that it's defined modulo 2 pi, but to do a modulo 2 pi difference, we would have to do a gauge invariant, and therefore there will be A's.
Yeah, absolutely. So very good question. So I've sneaked this in without really talking about it, but you're completely right? It is most obvious that this thing is defined only modulo 2 pi if I work in a gauge where A is set to 0, right? And then it's just phases of the order parameter, and clearly it's only defined modulo 2 pi. But that fact can't change when I change the gauge, and the way to see that it doesn't is to remember the form of the gauge transformation. Right? The gauge transformation, which I will now remember and get a sign wrong in, but please correct it. Right? So the gauge transformation is that A goes to A plus gradient of a scalar, and theta goes to theta plus that scalar up to constants. Yeah. So it follows from this that the integral of A along a path goes to the integral of A plus grad chi along a path, which is the original integral of A along a path plus the change in this chi between the two ends of the path. But theta right minus theta left will go to theta right plus chi right minus theta left minus chi left. And that is theta right minus theta left plus, yeah, I told you I was going to get the signs wrong. Like, you'd think 50% of the time I would get the signs right. This is weird. Yeah, so actually that's minus, this is plus, so this is minus. And so if I make a change of gauge, yes, I can change the relative phases of the two sides, but that change is completely cancelled by what I have to do to the vector potential in the middle.
Yes, but therefore we won't have. I can see a change of gauge such that delta theta is delta theta plus 2 pi after this gauge transformation.
No, because the gauge transformation doesn't change this delta theta.
Yeah.
We've just proved that. So here's a way of seeing it which might help. We've got two things we can do that don't make any difference. Right? Gauge transformations don't make any difference to the physics. Changing the difference in thetas by 2 pi doesn't make any difference to the physics. So if I go to a gauge where A is 0 in the junction, then that phase difference is whatever it is. If I change my gauge then it's still whatever it is because this form is gauge invariant. If I change the phase difference by 2 pi in the gauge where a equals 0, that doesn't make any difference.
But isn't there a continuity between theta L and theta R?
No. So the argument is no, because we have this junction in between. So consider the case where the junction is infinitely wide. In that case, I have two samples of superconductor separated by an infinite amount of vacuum.
Yes.
There's no requirement then that theta R and theta L should have any particular relation to each other.
Yes.
So we're really thinking of it from that point of view. Start with two superconductors at opposite ends of the universe, bring them slowly together, and ask, at what point do they notice each other and what consequence does that have? And actually, it's this current that eventually would provide the mechanism for locking the phases of the superconductors together, right? Because the current costs energy, and that energy will be minimized when the current is not flowing, and that's when the phases have locked. So if I have any dissipation in the junction, actually this is going to be the mechanism by which the two superconductors phase lock. But I'm asking about the beginning of that process when they've just been connected.
So if you want the only physical thing, quote unquote, is the condensate wave function, which doesn't have theta in it, but e to the I theta. So it cannot make any physical difference if you just start calling theta plus 2 pi.
Okay. And there is no chi inside the oscillating junction. It was,
Yeah, or like it would be e to the I chi.
Yeah. Okay.
About like 15 minutes ago, we made the argument that there is no field inside the junction.
Mm-hmm.
Now there's a current flowing through the junction. Doesn't this current produce a field?
What an awful question. By awful, of course, I mean good. Evidently it must. So then the question is it large enough to mess up our previous argument about the path and the gauge invariance? I think the answer to that probably depends on how broad the junction is, right? If the critical current determines the size of the current I run, if the critical current is reasonably large, then, at some point, yes, you will get into a regime where the current that you're running is large enough to affect the field. But I think before that, you'll get into a regime where you can no longer regard these as connected by weak tunneling, which this analysis is sort of based on in the first place. So this is really a calculation which is best in terms of consistency when the junction is very broad, the critical current is very small, and you can see this sinusoidal dependence on the phase difference, but without much back action on the field configuration in the junction. But again, that's an idealization. I actually don't know much about what happens, how this is perturbed in the case where the coupling through the junction gets stronger, but presumably it will be. I'd imagine that this, for example, will pick up higher harmonics, and maybe that's describable in the same language as the current is starting to generate fields in the junction.
Yeah, you said that you will equalize and lock the phases of the two sides if you have dissipation in the junction. Mm-hmm. All your intuition would say that, if it's a supercurrent, mm-hmm. We're saying that it's the steady state. We maintain the two phases and the supercurrent stays forever. Yes or no? Yes, that's what the equations are telling us.
Yes, that's right. But the question is, how are we maintaining the two phases? So I might, for example, have this superconductor wrapped around in a ring with some magnetic flux through it, which forces the phases to be different on opposite sides of the junction. And in that instance, yes, I'll maintain that phase difference because that's then a kind of boundary condition effect. And ultimately, I'm maintaining that phase difference by keeping the current running in my coils, which is making that field. If, however, I have two isolated lumps of superconductor and I just bring them together and connect them, then this mechanism will equalize their phases, because then there's nothing in that setup to maintain the phase difference.
Right, so good. So even if it's a supercurrent, it doesn't require dissipation in the junction to equalize the phases.
It probably does, because otherwise it would just keep oscillating.
Yeah, that's right. It'll need to, yeah, exactly. It'll do kind of Rabi oscillations unless there's something to make it settle. But I'm not sure, I mean, it's Cooper pairs tunneling across the barrier. But I'm not sure one should regard that as a supercurrent in the same way as it would be in the bulk of a superconductor, because there's no pairing field there. They're only Cooper pairs because they went in together. I haven't thought deeply about this, but I think Attila's right. Some dissipation's necessary, or it'll just oscillate.
The oscillation comes in when you voltage bias it, though, no? And what are we seeing here that's told us we're going to get an oscillation? We have a sine function, but you could start with two different phase lumps, put them together. It's not clear to me from what we said that oscillates.
I think the argument for why it should is that there is a phase difference between the two sides, so when you first connect them, that will drive a current. Then you have to ask, what does the action of that current over time do to the phase? You're moving Cooper pairs across from one side to the other. And so there's a...
Clearly, yeah, that cannot go,
that can't go...
I suppose the answer is that you're then generating an electric...
A chemical potential imbalance, or an electrochemical potential imbalance. And that will,
fair enough.
with dissipation, that will level, and it'll level at a point where the phases are equal. Without dissipation, it will oscillate.
Fair enough, yeah. Thank you.
Good. Please.
So we guessed away the only information we had about the width of the junction.
That's right.
So does the amplitude knows about the width then?
This knows about particular properties of the normal state of the junction which do depend on its width. Let me say a word about that. So I was going to give you the formula for that critical current. So the critical current in a calculation by Ambergaukar and Baratov, which you can tell was done before 1991 because this is the French spelling, is given by pi delta over 2e times Rn, where delta is the superconducting gap. We haven't actually defined the superconducting gap yet. That's going to come out of the BCS theory when we think about what excitations we see in the system when we break these Cooper pairs. But roughly speaking, you can think of this as being a sort of measure of this bulk value of the condensate wave function. That doesn't quite work out in terms of units, but roughly speaking, that's the idea. We'll do more details on that. And this Rn is the normal state resistance of the junction. And so that, of course, will know about parameters of the junction, including its width. You might ask, where does this formula come from? Well, I mean, the answer, as always, is more detailed calculation than we're doing here. But to understand roughly why it should look like this, 1 over the resistance is some measure of the transmission probability through the junction. And we know that in the end, this is, the superconductor is made of Cooper pairs, and so for 2 superconductors to talk to each other in a phase-coherent way, they have to move Cooper pairs coherently across from one side to the other. The probability for doing that must be related to the transmission amplitude. And so you can sort of argue that the 2 ingredients we have here in the critical current make sense, in that except for the constants, you get a higher critical current if the superconductivity on each side is more robust intrinsically, and you get a higher critical current if the 2 sides can talk to each other effectively, i.e. if the transmission probability for Cooper pairs is high. And since a Cooper pair is just made of 2 electrons, and the junction can't tell that it was a pair rather than just 2 electrons, the transmission probability for Cooper pairs is just related to the transmission probability for single electrons, which the normal state resistance was measuring.
But this assumes that both superconductors are the same material.
Yeah, that's correct. So there's a more complicated version of this. If, for example, they're 2 different S-wave superconductors with different gaps, or indeed if they're non-S-wave superconductors, I mean, then the orientation of the order parameter with respect to the junction matters a lot. And we will come back to that a bit when we talk about spatially varying order parameters, because an important class of experiments to demonstrate that you have an unconventional order parameter use this effect. Pardon my cough. So that's really more or less all I was planning to say about the Josephson effect. I would think of it as a sort of natural generalization of this formula here to the case of finite phase differences rather than small phase gradients. And of course, in the bulk of a superconductor, if I have a finite phase difference, I can always just look over a smaller distance and it will become a gradient. But in the case of a junction, I can't look over a smaller distance because there is a finite width to the junction and there may be a finite phase difference across it.
Can I ask, I'm sorry.
Yeah, there was one behind you.
Yes.
Okay. So in this case, because you have Cooper pairs going from one place to the other one, I guess that eventually this movement of electrons to the other side will change somehow the phase difference between the 2 and will go to 0.
Yeah, exactly. So yeah, we were talking about that possibility when we were talking about these oscillations.
But
So
we also have dissipation in between. So I think it's a more complicated thing. There should be some sort of combined effect between IC being reduced and delta theta, so to say. So because we have the 2 things at the same time. Some Cooper pairs going to the other side, but some dissipation in between.
yeah. So I mean, to describe it properly, you need to do some proper dynamics that have that information in. Again, we're doing one of these arguments where we say, well, the only place it can end, if there is any dissipation, is where the phases are equal. And that's assuming, as per earlier discussion with Andy, that there's not something keeping them unequal. Right? So it's analogous to a case where I connect 2 plates of a capacitor through a wire. We often pretend that the capacitor plates are infinitely large, and so the potential difference survives forever, and so that we get a steady state current in the wire. In the end, of course, the charge equalizes and the battery is drained. So in non-equilibrium problems, there are always these kind of subtle issues of which order you take limits in. And this is a problem like that, right? If I take the superconductors to be infinitely large before I connect them together, then the time scale for the equalization of the phases is infinite. And so then I can just say, well, a steady Josephson current will run forever. and it will depend on that initial phase difference. But in reality, of course, at some point it will drain. A good opportunity to give on camera Feynman's definition of equilibrium, which is when the fast stuff has finished and the slow stuff hasn't started yet.
Yeah, I had a coarse philosophical question.
Go for it.
Why did you do this now before going microscopic, given that you actually, as you said yourself, I think Josephson used BCS theory to derive it in the first place?
I guess because it relates. I guess because it had an important effect on the way people thought about the meaning of the entities in the Ginzburg-Landau theory. So it sort of belongs to the discussion of what does this complex order parameter field mean? What does the vector potential mean? It's another case where we have to think carefully about the interplay between those. And you might have been tempted to say that if the global phase in a superconductor is not defined because of gauge invariance, then there can be no physical phenomena that depend on phase differences because the phases themselves are not defined. So it seems important to mention it at this point because lots of people reacted to Josephson's prediction by saying, well, that can't be right because the global phase is not meaningful. So it seems worth emphasizing while we're still at the long wavelength, non-microscopic level, that there are experiments that allow you to give some gauge invariant meaning to the notion of a phase difference between two superconducting bulk samples. Yeah.
So I just wanted to ask a bit about the the AC Josephson effect. So we had all this discussion about trying to choose a gauge where the path integral term is negligible. But if I want to do the AC Josephson effect, the simplest seems to be to implement the electric field as dA by dt, and then all the work would be done by that second part. So are there any problems with doing it like this, or?
Not as far as I know. No, I think that works. I mean, there should be no problems in always using the fully gauge invariant expression. It's just, it makes the calculations longer and people often choose not to. And it's fine obviously to pick a gauge if you are perfectly confident that you haven't made any mistakes or any approximations that will break gauge invariance. But I always think for presentation purposes, it's important to emphasize that, and to re-emphasize that all of the observables really depend on gauge invariant things. But yeah, I think for the AC Josephson effect, that would work.
Yeah, so if we are saying that a phase difference is induced in a current, shouldn't the same thing happen within one superconductor that has a position-dependent phase?
It does.
So between parts of the same.
Yeah, exactly. But that's exactly what this equation tells us. That if this object, which is basically our gauge invariant phase gradient, is non-zero, then a supercurrent will run in the direction that it indicates.
Even though I don't have an external field or something?
Yeah, even though So for example, consider the case where I set up a supercurrent in a ring and then leave it alone. Right? That persistent current runs forever because I've built a gradient of this form into the wave function. Yeah. Good. There were others. Yeah, Paul.
How do you get to a state where you actually have different phases other than applying a magnetic field? Because I mean, if you just take two superconductors, you would never quite know that they will have a different phase before you bring them together, right? So, is there some way to achieve a phase difference other than just putting them in a magnetic field to basically fix the boundary conditions?
I mean, I think if you take two superconducting samples and you cool them down from their normal states, not in contact, and then you bring them into contact, then the phase difference will be some random number. And that feels weird because it feels like each superconductor picked a phase. But that's not true. The pair of superconductors picked a phase difference. So I think it's, I mean, you certainly see this in, I mean, okay, this is a superfluid example, but I think it would be the same for superconductors. If you know, they do these experiments where they take two Bose-Einstein condensates or two atom clouds, prepare them in different wells of their trap, push them through the Bose-Einstein condensation transition, and then do matter interferometry and let them interfere. And the phase of those interference fringes is different every time you do that experiment, which is the analog of this Josephson current being different every time you cool a couple of lumps of lead and then put them on the side of a bit of plastic. I don't know whether you really use plastic for these things. It's probably aluminium oxide, isn't it, really? Other questions? Okay, so that marks the end then of section 2. We have talked about writing an effective theory for charged bosons. We've seen that a phenomenon like condensation still happens, but that it's importantly different from the way it was in the superfluid. In particular, there is no breaking of U1 symmetry when the material goes superconducting, and you can see that there isn't because there is no Goldstone mode visible in the specific heat. The superconducting ground state is unique. We've seen some phenomena associated with its response to fields, the Meissner effect, the introduction of vortices if the superconductor is type 2, and we've seen that this short distance gradient expression for the supercurrent has a generalization to finite gauge invariant phase differences between different superconducting samples put in contact with each other. But hanging in the air is the question, where did these charged bosons come from? Because we know that in reality, these superconducting materials were made of a fixed crystal of positive ions and some mobile electrons. Everything in that system is a fermion, or at least with 50% probability, everything in that system is a fermion. And so where did the charged bosons appear from? And of course there's a hint from the fact that we've been writing the charge of the carriers when we couple them to the vector potential as -2e, which strongly suggests that somehow these charged bosons are made of pairs of the conduction electrons. But that's crazy because conduction electrons are both negative, so surely you shouldn't be able to just make a bound state out of them. And that's what the next bit of the course is about. How did we make those bound states in conventional superconductors? And how is it possible for them to condense? And you might say, well, obviously they can condense once they're bosons, but actually what we'll find is that the bound states are very big. So that's one of the puzzles that BCS solved. How is it that when the bound states are only very weak and therefore much bigger than the spacing between them, right? So in a Cooper pair in a metal that's about to go superconducting, frequently there are many hundreds of other Cooper pairs kind of occupying the space between the two paired electrons. So these really can't be thought of as kind of more or less point-like bosonic molecules made of these electrons. They're in the opposite limit. And the question is, in that limit, how do I get something that looks like condensation? It's clearly not as simple as just saying, well, they're now basically bosons because I've bound two fermions together, because I've bound them too weakly for that argument to work. Good, so that's what the next bit's about. And there are basically 3 key papers which happened in 3 consecutive years here. There was a paper by Lilo and Pines in 1955, which argued that it was possible for effects of lattice vibrations causing an attraction between the electrons to overcome the Coulomb repulsion at sufficiently low frequencies. Then there was a paper in 1956 by Cooper which pointed out that Right, so you might think attractive interactions are not enough because if you remember your undergraduate quantum mechanics, a weak attraction in 3 dimensions doesn't make a bound state. Right, so you may have been asked to prove this at some point. Arbitrarily weak attraction makes a bound state in quantum mechanics in 1D and in 2D, but not in 3D. You need a threshold strength of attraction. So just getting a weak attraction wasn't enough. But Cooper showed in 1956 that that argument is crucially altered by the presence of a Fermi surface. So 2 electrons in free space subject to a weak attraction would not form a bound state, but 2 electrons in the presence of a Fermi sea do. And that's a sort of scattering restriction effect, and we'll do a little calculation to show how that works out. And then the key question was, okay, we've shown that a pair of such electrons with an attraction form a bound state, but that bound state is very big. How is it that an entire chunk of the Fermi surface manages to do this and then condense in some coordinated way? And Bardeen, Cooper, and Schrieffer in 1957 wrote down a candidate state in which the electrons have done just that, which is called the BCS wave function, and that's the thing we're going to go on to discuss, and how it, well, firstly, how it gives rise to the properties that we've seen for superconductors in the second part of the course, and also what other things it predicts, like results of point contact tunneling into superconductors, and that kind of experiment. Okay, so there are 3 ingredients which are 1, effective attraction due to lattice vibrations. So the fact that the electrons are moving in a deformable medium turns out to be really important. 2 is the Cooper instability, which says that in the presence of a Fermi surface, we get a bound state for arbitrarily weak attraction. And I guess it's important to emphasize the dimensionality, because that fact wouldn't have been a surprise in 2D or 1D, but it is a surprise in 3D. And then the BCS wave function for a condensate, I'll put it in quotation marks and we'll discuss later whether I should have done, of Cooper pairs. And the reason why you need a special wave function for this is that the size of the Cooper pair is actually much greater than density to the minus 1/3, which is the typical spacing between Cooper pairs. So that's not the Bose-Einstein condensation limit, it's the opposite limit, where the Cooper pairs are very big, and so we have to think about how something like condensation happens in that case. Okay, so item 1 is, how did we get the attraction? And before writing down any formulas, I just want to talk about the basic physics of this. We're then going to sweep the essential physics completely under the rug and write a simple model which doesn't contain it. But it's going to be important when we come back to talk about unconventional superconductors and what kind of order parameter symmetries we expect there. So the basic physics is the physics of retardation. So the way I think about this is, imagine an electron moving through a material. It's actually interacting with two different bosonic fields. It's interacting with the electromagnetic field. So as it moves, it's creating a Coulomb field around itself, and it's creating a little bit of magnetic field as well because it's a current. And it's also creating a distortion in the lattice because the ions are positively charged and the electron is negatively charged. Now, of course, those are related because it's creating the distortion in the lattice via the electromagnetic field. But the point is that the disturbance that the charge makes in the electromagnetic field in a given place dissipates very quickly after the charge has left, but the disturbance that it makes in the lattice lasts for a long time. So if I had to say, imagine that I have a region of the lattice and an electron passes through it at some time t equals 0. I can ask, what is the effective attraction of another electron to that place later? And of course, very shortly after this passes through, the Coulomb field that it generated is still there. That's much stronger than any small adjustment of the lattice, and so I'll get strong repulsion at short times. But then that goes away quite quickly, and I will cross over at some point to a point where the sort of excess positive charge of the lattice that was dragged in by the first electron is still there and acts as an attracting centre for the next electron that comes along. And so there's a time scale on which this goes negative, and of course over time it will then eventually go to 0. So that mismatch of timescales is absolutely crucial to the development of this effective attraction, at least in conventional superconductors. It's the fact that the lattice is heavy and slow compared to the electromagnetic field, which means that the imprint of the first electron can stay there and effectively attract the second.
I mean, many people would say that the fast time scale is set by the electron velocity, not by the... I mean, if the electron's going slowly... That's fair. So I've drawn this for an electron passing through at infinite speed, which is, of course, unrealistic. That's... So in many ways, it's the scale difference between the Fermi velocity and the sound velocity.
Yeah, that's fair enough. Yeah. So there is a period of time when the electron has gone, and therefore its field has gone with it.
Yeah.
But a distortion in the lattice is left. Yeah.
So probably it's on, if you use your language, it's almost 3 scales. There's the time scale of the Coulomb interaction.
Yeah.
There's the velocity of the electrons, and there's the velocity of the lattice.
I agree. And it wasn't physical to draw this as if the electron velocity was infinite. Yeah, good. Yeah.
I have a very stupid question to this.
Good.
So if the time scales are so different, so why just 2 electrons form a bound state? Why not more?
Yeah, very good question. So the basic answer to that is that if you want to, so the lowest energy bound state is going to be one that's at rest. And you can only form a bound state at rest out of an electron and its counterpart with the opposite momentum. If you try to form bound states out of an electron and another one, then the bound state that you form will also have some centre of mass momentum. And that's enough in typical circumstances to make it not worth doing. Right? So the energy you would have to pay to put the eventual Cooper pair in motion, or the energy that would cost, is greater than you get from making the bound state in the first place. So we'll see more of that when we write down the microscopic theory.
But she was talking about, you're saying you pair and you can make a pair at rest. Mm-hmm. You're saying if you make it a triple or a quadruple, then you cannot have the whole thing at rest. I mean, she was asking about, I think, multi-particle.
Yeah, okay, so you're imagining, yeah, if this, once I've made a Cooper pair, why can't I give this argument then for Cooper pairs moving around? When Cooper pairs are charged, they will distort the lattice, and that should drag another Cooper pair in and make a 4 fermion object. Or 3, right? Yeah, I could make a spin half object which was an electron bound to a Cooper pair. So I don't know if this is a complete answer to that question, but one of the things that prevents that from being the right reasoning is that at least in this weakly attractive case, as soon as I form the Cooper pairs, they condense. So there's no range of temperature where I have, at least in this weakly attractive case, where I have the Cooper pairs, but they haven't formed the condensate. And once they've formed the condensate, I can't think of them as individual particles moving around like wave packets. They've all gone into a sort of common motional state. And that motional state also involves the phonons, right? I mean, if you really ask, what's the superconductor made of? It's made of the electrons that made the Cooper pairs and also the lattice vibrations that are coherent with them. And there's nice literature in the 50s about how much of the superconducting condensation energy is actually a reduction in the energy of the lattice degrees of freedom and how much is a reduction in the energy of the electronic degrees of freedom. So I think at least in BCS theory, at least part of the answer to the question is once you pair a pair, you get the condensation.
But also, sorry, just to complete this, also the pair is quite extended, right? I mean, like the charge is no longer localized at one place in real space anymore. So that I think also contributes.
Yeah, okay, so because the pair is so weak, I can then not think of a Cooper pair as moving through a small region of the lattice because the Cooper pair is very large.
It's not a point-like object.
And maybe those answers might even be related.
But also, I mean, it is a nice picture if you had like a single electron and another electron, but I mean, once another electron is going to move there, then there's a much stronger force pushing every other electron away, right? I mean, basically, if an electron sits in this minimum, then there's a negative charge already taking this away. So it's kind of, I mean, it's a nice intuitive picture, but I think it breaks down once you put an actual density of electrons. That I mean,
Yeah, I mean,
very careful about.
I think the intuitive picture would tell you that they should make chains, right? So the first electron goes through. At some time later, that site is attractive to another.
Yeah.
The second electron arrives, it maintains the lattice distortion by passing through that site, then a third one will get drawn after it. And yeah, so, I mean, what that's telling us is that there are limits to these classical pictures of what's going on, right? I mean, really, we're not making real lattice distortions, we're causing the lattice to fluctuate quantum mechanically into one of the distorted states available to it, and that is a bit different.
But what about the Cooper instability problem? Is there not going to be some difficulty with getting a multi-particle bound state for an arbitrarily weak interaction?
So that's sort of what part 3 would do. So the BCS wave function...
I mean a multi-particle Cooper pair, right? So we stay at the Cooper problem level, and he showed... Well, I have no idea if this is right or not, but you wonder, he showed that because of the presence of the Fermi C, you could pair up for arbitrarily weak interaction. But one would probably need to look at how he got that to see what the spectrum would be for triples or quadruples.
Yeah. Yeah, I've never seen an attempt to do that calculation, but certainly you should be able to ask that. I wonder whether it ends up being like in... what we were discussing with vortices, that the extra correlation that you have to put in to make a 4-particle bound state doesn't really gain you much energetically And so you're better off having two particle bound states moving independently of each other. But that's a guess. I've never tried to make that comparison.
The real answer to Simile is that we gave up trying to think about those things when we had extremely good physical evidence that it was up here.
Indeed, but it's good to ask, right? Because yeah, you're absolutely right. This cartoon argument would tell you that all the electrons in the material make a chain or something like that, and that certainly doesn't happen. Yeah, so it's a good question whether already at the Cooper problem level you can see that you prefer to make two particle bound states rather than one 4 particle one. I'll see if anyone has tried to do that, because I know there are, in some cold atom circumstances, you do stabilize Cooper quadruplets or something of that sort. So it's not always completely impossible, and so probably those papers discuss when it is and when it isn't, and we discover that here we're in a regime where it doesn't happen.
But in cold atoms, isn't this done with attractive interactions?
Yeah, so that's another question, but actually we'll discover, so this aspect of the retardation is really important for the physics, but isn't in any of the calculations. So Cooper's calculation was for weakly attractive particles full stop. And that's because basically if you actually have to put retardation in, you can't write Hamiltonians because that stuff's all local in time, and the calculation just becomes unmanageably complicated. So what they actually did more or less immediately was to replace this with an approximate model where the electrons were considered attractive if they were close enough to the Fermi surface. And that allows you to write something that's local in time. But you can certainly ask, how good a cartoon of this situation is the instantaneous model that Cooper worked with and that BCS worked with. And there was a lot of argument about that at the time. And a lot of the motivation for the kind of more field theoretic analyses of these things that was done in the 60s was that worry that that something very crude had been done in this theory in the late 50s, replacing the retarded interaction by an instantaneous attraction, and maybe that completely altered the physics. It turns out it doesn't, but that's not obvious at the point where this is being done.
But we still have myriad of models nowadays that are not BCS models of superconductivity, right?
Yeah.
So the general considerations that you gave about why is a superconductor different from a superfluid, the coupling to the electromagnetic field and everything, they're all beyond BCS theory.
Absolutely. Yeah, absolutely. But as an account of, you could doubt the applicability of the Cooper calculation as it was done, or the BCS state as it was written down, to any superconductor that they knew of at the time, because of this retardation stuff that was just... Yeah, but no, I agree. So the broad phenomenology is to some extent independent of the answers to these questions, which is why we covered it first. But people did still care about the answers to these questions.
So actually, to answer Andy's earlier question, I'm aware that some people in Cambridge a little bit before my time that did like a calculation for spin imbalanced Fermi surfaces, and there they found that like pairing bigger clusters so that they try to match the ratio of the imbalance. So like if you have a 2-to-1 imbalance, then pairing 2 up and 1 down electron can be beneficial. I don't know if much came out of it, and also it's not a very realistic setup. But
that was Gareth Conduit's stuff, yeah. I remember hearing him talk about that at some point. Yeah. Yeah, so there seem to be cases where it does do other stuff. This isn't one of them. And it's not clear to me whether the answer is because at the Cooper level it's not worth doing, or because condensation just kicks in first. But we'll think about that and bring things back. Good. Other questions? Okay, so this is basically the rough physical argument. And to hang some flesh on the bones, you need to do a calculation in perturbation theory to ask, you know, what happens if I take the conduction electrons and I couple them to the lattice. So I'm just going to show the result of that calculation. It's described in Derek Lee's notes and in James Annette's book and in lots of other places. So let me make it clear that this is a result of a certain type of perturbation theory. And the result is that there is an effective interaction, which I'm now going to write in wave vector and frequency space, which I realize is not natural looking, but it's sort of where you have to do these calculations. So this is the effective interaction. You can think of this as basically the interaction, the probability that an interaction transfers a momentum q from one electron to another with a time delay given by 1 over omega. And so it's relevant to this, and the frequency dependence of this will mimic the time dependence in this graph. Right, so we'll find that at high frequencies, which is equivalent to short times, the interaction is repulsive, and at low frequencies, which is equivalent to long times, the interaction becomes attractive. And so it's just a sort of Fourier representation of this graph. Yeah, Barrett?
Is Q then a relative Q between two particles?
Yes. So it's the momentum transfer from one to another in a scattering event. So this is generally how you should think of interactions in Fourier space. You should think of sending in two particles with definite momenta. The interaction causes them to exchange some momentum. And so the Fourier transform of the interaction potential is basically the probability for exchanging that amount of momentum in a scattering event. So, if we just had electrons in free space, subject to the Coulomb interaction, this would look like this. So that's just the regular Coulomb potential, E squared over 4 pi epsilon naught r, Fourier transformed. The Fourier transform of 1 over r is 1 over q squared. That tells me that by far the most likely scatterings in Coulomb systems are small angle scatterings. And this is because the force is long range, so it scatters particles even when they're a long way away from each other, and those scatterings are small angle. But of course we're inside a metal when we're thinking about developing the superconductor, and we know that in a metal the Coulomb interaction is screened. So it's no longer 1 over r, it's 1 over r with some exponential cutoff set by the Thomas Fermi screening length. And so people normally put that cutoff term here, where this psi tf is the Thomas Fermi screening length, which is the length scale over which, the length scale beyond which you can't see an additional negative charge in the metal because of the screening cloud that's formed around it. So, for the purposes of this discussion, we're assuming that that screening is instantaneous, right? Because the electrons are quick. Really, it's given by some Fermi velocity factors. So this is already an approximation. We've approximated the kind of screening of electrons by other electrons as infinitely fast. And the only real frequency dependence we're going to care about is the stuff that comes from the phonons. And what happens when you add phonons to this problem is you get a leading term which looks like this screened electron-electron interaction, and then the inclusion of scattering interactions with the phonons gives a term that looks like this, at least in some commonly used approximation. Omega q is the phonon dispersion relation. Obviously that may have several branches actually. We've done this calculation for just one branch of a phonon dispersion, but it's not difficult to add more terms like this to account for the influence of other branches. And yeah, as mentioned, this psi tf is the Thomas Fermi screening length of the metal. which depends on various parameters like electron density and so on, but let's not do that on that. So if we ask how does this function behave as a function of frequency, which is the bit we really care about, so what I'm now going to do is to fix Q, the momentum transfer, and ask for a given momentum transfer, how does this interaction energy change as I change the frequency? So if Q is fixed, omega Q is fixed. So at a given Q, I have a particular phonon frequency. For frequencies much greater than that, this denominator is large and positive, so this fraction is more or less 0. So at very high frequency, we just get back to the regular screened Coulomb result. So this value is some E squared over epsilon naught 1 over Q squared plus Thomas-Furby screening length 3 minus 2. Then, as omega is reduced towards omega Q, this tends to 0 from above, which means that this factor tends to plus infinity. When omega is less than omega Q, it comes back on at minus infinity. And you can see that when omega is 0, this term exactly cancels that one, and it approaches 0 from below. So that's the representation in frequency of this graph here. At very short times, we have a constant repulsive interaction given by the screened Coulomb effect. As this gets closer to the phonon frequency, we get a resonance effect where the repulsion gets stronger and stronger and stronger, and then when we go below the phonon frequency, it kicks over into attraction, and that attraction persists all the way down to 0 frequency, which is infinite time, although of course it tails away because the lattice is also relaxing.
Say it's equivalent. I can see lots of equivalents, but I don't see the repulsive thing tending to infinity.
Right. So, in some sense, the issue here is that when we think about scattering, we're thinking about scattering an electron wave. And here we're looking at a momentum transfer. We're looking at a momentum and energy transfer in the scattering, which is resonant with the phonon mode. So we know that the lattice system can sustain completely undamped oscillations in this model at that frequency of momentum transfer. So you could just keep pumping energy into the lattice if you pump it in at that frequency of momentum.
Yeah, I'm not really, all I'm saying is you made an analogy between what you showed there and the graph above, but that is not a perfect analogy.
No, that's absolutely right. So, of course, what we didn't discuss in this graph is the fact that the lattice is not actually a damped system in the way we normally model it. So we had a picture in this real space picture of some local distortion forming in the lattice. But, of course, the point is if I locally distort the lattice, that will propagate to the neighbours, that will propagate to the neighbours. And so if I get my frequency and momentum just right, my passing electron can disturb the entire lattice, and that leads to a very strong correction to the interactions. Now, obviously, that's an artifact of the approximations that have been made here, right? Those lattice vibrations would then scatter other electrons and will become damped, and this will get rounded off into something that looked more reasonable. But at the level of the calculation that people normally do, this is a legit resonance because we haven't put any damping into the phonon system.
But so the calculation to get there, just a bit of overkill maybe, but it's really you make perturbation theory of basically the two electron correlator. Like if you were to draw.
Yeah, that's right. So this is a perturbative set of perturbative corrections to the vertex.
Okay, so basically you really, in terms of Feynman diagrams, you have 2 electrons going in, then stuff, and then 2 electrons going out.
Yeah, exactly. And you're summing up a particular class of diagrams that correct that vertex.
And you consider both the photon and the phonon in there to get this, because the phonon gives you the...
Yeah, that's right. The phonon gives the screen.
So, can this functional form be measured in experiments?
That's a great question. I mean, the naive thing to do would be to, yeah, okay, but we need frequency, right? So it's not so easy.
How would you do that? Like shoot an electron onto a sample, or?
I'm just asking, can it be? I'm not saying that it can. Or
I guess what you would want to do is to, yeah, I mean, if you could arrange an experiment where you sent in 2 electrons with a well-defined, with well-defined momenta. So you have some source on the edge of the sample, you spit 2 electrons in. Those will make wave packets. The wave packets will last for a reasonably long time because the metals are Fermi liquid. They will have some scattering interaction and they will come out somewhere. Now, I guess the problem is, how do you see electron wave packets of charge 1 against a metallic background? I mean, it's in the end... Sorry?
With an STM.
Well, I don't think you do, though, do you? I mean, what the STM sees is really disturbances in the electron density caused by impurities and things, and that's a kind of collective response. So I don't have a good experimental protocol for directly measuring this. But yeah, so you might ask, how good is our evidence that this is the right expression for the effective attraction? It may not be that good. I mean, it turns out anyway that to proceed with the calculation, we can't use anything as functionally complicated as this. So we end up replacing it by a much cruder approximation anyway. So in a sense, if this isn't exactly right, it kind of doesn't matter. What it has to be right about is that there's some range of frequency where the interaction is attractive. So we could, without doing this, have just said, well, clearly there's some range of timescales where the interaction's attractive, and just written something down as an effective model. But I guess people like this presentation because it at least is some legitimate output of a calculation where you look at the phonon effect on the electrons.
How do you think about the asymptote at omega q? Like what's like the physical intuition for what is the potential there?
I mean, really the answer is, beyond a certain point, there's got to be unphysical. So what we've done is to keep in the calculation a certain set of processes where the electrons temporarily transfer energy and momentum to the phonons and then get it back. What we haven't included are processes where, after that transfer to the phonons give it to other electrons, which of course, when the energy gets high enough, will surely happen. So, in some sense, you should probably regard this calculation as being unreliable anyway, in some window around the resonance, which will, there you have to take damping effects properly into account. But the argument is that actually bound state formation is happening for very low energy electrons. We sort of know that because it's happening at very low temperatures. And so the bit of the graph we're really going to care about is this one. And the argument is that whatever you put in to kind of round off the resonance in terms of extra physics, this feature that the approach at low frequencies is from the attractive side is probably going to survive.
So this assumption of a metallic sample or a Fermi surface, is present everywhere, or are you just talking now, or is it also present in BCS?
It's present in BCS theory as well. So
It does work well for insulators which turn superconducting, right?
yeah, and I mean also straight superconductors that form out of strange metals that don't have sort of an obvious thing that you would call a Fermi surface in the sense they don't have quasi-particles. Yeah, I mean, that's right. So, in a way, you know, imagine that I had a material that made a transition from a ferromagnetic metal to an antiferromagnetic metal. I could argue then that the transition is from one ordered phase to another. However, I could still motivate the fact that an antiferromagnetic metal happened by saying if I had a paramagnetic metal, that it would have an instability to that. So what this argument really is going to establish is that at low enough temperatures, the BCS superconductor is a better state energetically than the Fermi liquid, or is a better state free energetically than the Fermi liquid. Now, of course, if you have some third state in play, a strange metal or whatever, then really you have to do another bit of the calculation and ask, well, do we know that the strange metal is unstable to superconductivity? And so it could be that you have a Fermi liquid state and a superconducting state. At some temperature, their free energies cross over. So in the absence of anything else, you would say there's a transition. But maybe there's some third state that the system could be in, maybe an insulating state, which beats both of them at all temperatures, and then your system is just an insulator. So all we can really establish with these instability arguments is that one state that we're considering has lower free energy than another state that we're considering. It doesn't directly tell us about sort of third or fourth competitor states that the system might want to go into. So yeah, that's as much as this calculation can do. Yeah.
And there are metals that don't go superconductor even at an arbitrary low temperature. So where does this argument break down for those?
So for clean metals, I believe the theoretical statement is eventually they will. So there's an additional complication actually, which is that in sufficiently clean metals, there's also another source of electron-electron attraction, which is the exchange of Friedel oscillations, which are oscillations in the conduction sea itself. So there's certainly a theorem by Kohn and Luttinger that says that even without phonon-mediated attraction, at sufficiently low temperatures, any clean metal will have a superconducting instability just because of the exchange of Friedel oscillations between its own electrons. But Kohn and Luttinger point out that a ballpark estimate of that temperature is nanokelvin, but that, it's in the exponent, so things could change. So yeah, the general understanding of why we don't see phonon-mediated superconductivity in many of the simple metals is just that we haven't been to low enough temperatures. And so what actually sets the instability temperature, we'll see that it's an exponential function of the electron-phonon coupling, so it's pretty sensitive. And so you only have to weaken the electron-phonon coupling a bit to push TC a long way down. Now, dirty superconductors are a different question. Right? So there is no theorem that says that a disordered metal will always go superconducting. Mm-hmm. And so there, if you have a disordered metal, potentially you can not develop it at all. But in the clean case, the prediction is that if nothing else cuts in first, the ground state is always superconducting, and if you haven't seen that in experiment, you're just not cold enough.
Is there in real life such a thing as a clean metal?
I mean, define clean.
Maybe Luttinger and Kohn did, I don't know.
Yeah. So, I mean, there's been quite a lot of work on the interplay of disorder and superconductivity. The answer is it depends on the order parameter symmetry, actually. So S-wave superconducting instabilities should be good up to quite high levels of disorder. Non-S-wave instabilities typically aren't. But Cone-Luttinger instabilities are often not S-wave. So actually, you probably disorder your way out of Cone-Luttinger quite early. Phonon-mediated superconductivity usually is S-wave, and so I would expect that your typical metal with, non-extreme levels of disorder will still have a phonon-driven superconducting instability, but then by the argument about the coupling constant, it may be at very low temperatures. Good. We should stop for lunch because it's after 12 o'clock. So basically that's point one, the effective attraction due to virtual phonon exchange. We'll reconvene on Tuesday, remember, not Wednesday, and in seminar room 1, not seminar room 4, to talk about the calculation that shows that this attraction, or a very crude cartoon of it, leads to bound state formation. Thanks everyone.